Hello and welcome to mini lecture number 5 on log plots, which are going to use the log functions that you learned about in the previous lecture to more efficiently plot curves. So this is one of the most complicated topics in this section of the course, so make sure you spend the time that you need with this lecture. If you need to revisit this video or do extra practice on these problems, make sure that you take the time to do that. All right, so let's start by talking about linear number lines. Number lines, this top one is like the number line that you're used to, the linear number line, where we have this value x. And that value x is evenly spaced, -1, 0, 1, 2, and so forth. These number lines are great, they're easy to interpret, but sometimes they can be inconvenient because if we wanted to plot 100, it would fly off of this page. So 10 would already be way over here, and 100 be way over on the right-hand side. So we can't easily plot both small numbers and large numbers on the same number line, linear number line, and have them both show up very well. So a log number line takes care of this by shrinking the large numbers, and spreading out the small numbers so that we can see both what's happening down here and what's happening up here at the same time. How do we do this? That's the hard part. So the hard part is saying, how do we plot things so that we spread out things down here and shrink things up here? Well, what we're going to do is instead of plotting x, we're going to plot log of x. All right, what does this mean? Well, in order to do this, let's just first take some logs. Well, first of all, what is the log of 0.1? Remember what this means? We have a 10 down here, and we're saying 10 to what value gives you a 0.1? Well, 10 to the -1 gives you 0.1. Similarly, log base 10 of 1 is equal to 0 because 10 to the 0th is 1. 10 log base 10 of 10 is equal to 1. Log base 10 of 100 is equal to 2, and log base 10 of 1000 is equal to 3. Log base 10 of 2 is equal to 0.3, and log base 10 of 3 is 0.47. All right, so suppose we have a red point here at 1. Now, where are we going to put that red point on our new number line? Well, if it's at 1 on the old number line, it is at 0 on the new number line. So this red point is going to move over to 0 on the new number line. So our red dot moves here. If we had a green dot at 0.1, where does that move? Well, that green dot is going to move down to -1 on our new number line. A black dot at 2 is going to move to the point 0.3 down here. And the point over here at 10, which we can't really draw on our linear number line because it would fly way off the page, moves over here to 1. So we're smushing the large numbers and spreading out the big ones. In addition, we can draw numbers that even really aren't on the page, like a yellow dot at 100 and so forth. All right, so we take the values that we have on the linear number line and we plot them instead where the log of their value is on the log number line. Now, some important details to realize about this. What happens if we take the log of 0? Well, if we take the log of 0, then it does not exist. So we cannot plot negative numbers on a linear number line, or on a log number line. A log number line has only strictly positive numbers, so numbers that are greater than 0. Anything down here maps to does not exist. Points that fall between 0 and 1, decimal numbers between 0 and 1, are now mapped to the negative numbers on the log number line. Things that are multiples of 10 on the linear number line are evenly spaced on the log number line. So our multiples of 10 here are 10 to the -1, 10 to the 1, and 10 or sorry, 10 to the minus 1, 10 to the 0th, and 10 to the 1, which are now evenly spaced at minus 1, 0, and 1 on our log number line. Okay? A log scale shrinks large numbers. It smooshes together numbers that are out here and spreads out numbers that are down here so that we can see them all on the same scale. All right. So log number lines are also useful in comparing numbers in terms of orders of magnitude. So the distance on a log number line between two numbers is their difference in the orders of magnitude. So if we have our log of x here in blue, here we have log of x of 0, 1, 2, 3, and 4. That corresponds to a x value of 10 to the 0, 10 to the 1, 10 to the 2, and so forth. The distance between 2 points on this log number line is going to be their differences in terms of orders of magnitude. To see how this plays out, let's do 2 examples. First, let's plot the points n1 equals 10 and n2 is equal to 10,000 on this log number line. Where do we put n1 is equal to 10? Well, we take the log of it, the log of n1. What value do you have to raise 10 to get n1 equals 10? Well, we have to raise it to the first power. So this is n1. Where do we put n2? The log of n2 is 4 because 10 to the 4th is 10,000. So we put n2 there. All right. What's the distance between this? It's 1, 2, 3. So n1 is 3 orders of magnitude smaller than n2. What about this next example? What if n1 is 250? 250, the log of 250. 10 to what number is 250? Turns out it's 2.4. The log 10 to what number is 100? That is 2. So n2 is here at 2, and n1 at 250 is at 2.4. So there's 0.4 distance between those two. So n1 is 0.4 orders of magnitude larger than n2. All right. So that is a log number line. If we want to plot on a log scale, then we're just going to combine different linear and log number lines on our x and y axes to be able to plot complicated curves that don't show up well on original plots into more reasonable axes. All right, so a good example of this is the function f of x is equal to 10 to the x. What happens if we plot 10 to the x on a linear plot? This is your traditional plot. It's going to look something like this curve. So as you know, with exponentials, or in this case 10 to the x, it's going to fly off the plot. So we really can't plot values of x that are over here. So what are we doing in this plot? We're plotting values of x against values of 10 to the x, which is f of x. All right. Now, what we're going to do in this next plot, which is called a log plot, is to plot the same x values against the log of the y value. So instead of plotting f of x, we're going to plot the log of f of x. So this is our x, and this is our new y. All right. So what was before at 1.11, which is way down here, is now going to be at 0.1, 0.1, which is that point right there. All right? What was before at 50, 10 to the 50th, which is way off this plot, is now at 50, 50. Okay? So we get that point there. And as you can see, we're going to end up with a line. So this is a normal property of exponential functions plotted on a log plot. That if you plot a log plot of an exponential function, you will get a line. Okay. Now we can take this idea even further, and we can plot something on the curve on a log plot. This means that we not only plot the log of the y values, but we plot the log of the x values. For this here, we're going to be plotting the log of the x values against the log of the y values. So those are the blue points. Okay, we get back the same kind of shape that we had before, but now we can capture a whole lot more points that we didn't have before. So what we had before, if we were trying to plot the red curve, if we plotted x equals 50, we couldn't plot 10 to the 50th. That would be way off this plot. But now, when we plot this, we're plotting it as 1.67, which is right here, 1.67, and we're plotting it at 50. So we're capturing points that we couldn't possibly capture on this plot, but we get the same kind of shape back. All right, now I want to point out something about the naming here. In math, we always name things as x, y. So if you have a coordinate pair, you have the x coordinate and then the y coordinate. Plots are the same way. So when we name plots, we tell you the x scale, then the y scale. So this is a linear plot. This is a linear log plot, and this is a log plot. So this is the x scale, this is the y scale, this is the x scale, this is the y scale, this is the x scale, this is the y scale. Now, some of these words we drop because if they are linear in the x, we drop that because that is the classic way of doing it. So the classic way of plotting is to have a linear x-axis, and so this word out here is often dropped. But if you're wondering what kind of plot it is, think about what is the x, what is the y. All right, so we plotted 10 to the x. Let's consider a second function, which is the log of x. So g of x equals the log of x. On a linear plot where we have a linear x and a linear y, this function has this curve here. Now, notice the scale of this x-axis. We go all the way from 0 to 1,000. So we really can't see what's happening down here at the same kind of detail that we can see what's happening up here. All right. So if we have some key points here, we're plotting this x against our g of x. This is our linear scale. So the point 1 is mapping to the point 0. So 1 goes to 0, 2 goes to 0.3, 2 goes to 0.3, 10 goes to 1, 100 goes to 2, 100 goes to 2, 1,000 goes to 3. So this curves down very sharply. There's this vertical asymptote where the log axis goes really steep, right? Okay, so next we're going to try to plot this on a log linear plot, which means we have a log x-axis, which we're going to smoosh together these values up here and spread out these values down here, because as you can see, we really can't see what's going on there. It just gets too steep. Okay, so here what we're going to do is we're going to be plotting a log x-axis, so we're going to take the log values of x and we're going to plot them against the linear values of the y. So we're taking these two columns. So the point 0 is going to map to the point 0. So 0 goes to 0. The point 1 is going to go to the point 1. So the point 1 is our old value of 10 is now 1. So what was at 10 over here is now down here at 1. So we have that point goes right there. The point that was at 100, 2, is going to now go at 2, 2. So 2, 2 goes right there. And the point that was at 1,000, 3, we take the log of 1,000, which is 3, and we end up with 3, 3. So we take this point, and where do we move it? We move it right down here. And we once again get a log line. So notice that if you plot a linear log plot of an exponential function, you get a line. If you plot a log linear with flipped of a log curve, you get a line. So oftentimes, when we take the log scale or a log linear plot of an exponential or log function, we'll get a line. Now, similarly, we can plot both the x and the y-axis on a log scale, and we're going to get back the same kind of shape that we had before, but we're going to be able to see points that we couldn't have seen before. So here, for this last one, we're plotting a log x-axis against a log y-axis. So we're able to see points that we really couldn't have seen before. All right. So finally, let's talk about how we label the x and y axes. So we either plot them on a log axis or on a linear axis, but oftentimes it's convenient to actually label the ticks and label the y-axis not as a log, but in the linear scale. So we've been working so far with log linear plots or linear log plots where we label this axis as an x and this as log of y. And then if we take the log of y, then this is 10 to the 0th. This is 10 to the 1, 10 squared, 10 to the cubed, and 10 to the 4th. Well, it's really inconvenient to do that because, as you can tell from my pausing, it takes a minute to double check yourself and to think about what these values mean if this is log of y. So even though this is a convenient scale to plot them on, it's not very convenient to label them that way. So let's actually label them with our original numbers and label this axis as y instead. So instead of labeling this as 0, 10 to the 0th is 1, so we're going to label that point as 1. Instead of labeling this value as 1, this is 10 to the 1, which is 10. This is 10 to the 4th, which is 10 to the 4th over here. All right, so the shape of the curve isn't changing. You're still plotting this on a linear log axis, where this is the x is a linear scale and the y-axis is on a log scale. But now we're labeling the ticks and labeling the y-axis with the original values. It just makes it one less step of interpretation to do. So just take a quick look whenever you're looking at a plot at what scale the axes are on and if they're labeled in terms of the original variables or in terms of the log variables over here. All right, so with that, I'm going to leave you with this self-study question. And once again, I'm just going to reaffirm that this is a really complicated, confusing topic. So take your time with this self-study question and really grapple with this concept, and I'll see you in class.